Before we finish with chi-squared, let's have a few final thoughts. First, this diagram, right? This again is our conceptual flow of what chi-squared is doing. It's allowing us to make this decision right here about whether our observations match the expectations formed by either our mathematical model or by assuming that two things are independent of one another. Chi-squared statistic is done by summing up these squared differences between the observations and expectations divided by the expectations. We have the same exact procedure as we did for f and t, where we have a null and alternative hypothesis, observed values, expected values. This is basically going to allow us to calculate our test statistic. The expected values come from these two different options. Then we have our test value. Then we have degrees of freedom. Then we use our table to get critical values or a computer to calculate the p-value directly. That allows us to get a p-value. If it's less than 0.05, then we reject our null hypothesis, which then either tells us the mathematical model is not making good predictions or the two factors we're looking at are not independent. Or we would accept our null hypothesis, in which case our mathematical model is doing a good job of making predictions, or it looks like our factors are independent of one another. So again, two types of chi-squared test, goodness of fit, where we use a mathematical model. Our degrees of freedom is our number of categories minus 1 minus the number of parameters we had to use our data to estimate. So it's not just the number of parameters, because in some models, the parameters are built right in, like in the Mendelian segregation example. It's the number of parameters where we had to look at our observed values and do some sort of calculation with them to calculate a parameter to put into our model. So for example, in the parasitized insects on leaves example from earlier in the semester, we had to figure out what the overall rate of infection was from looking at our data first. For the independence and homogeneity tests, the expected values come from predictions if the factors are independent of one another. So we made these grids. The example we did in the other lecture was a 2x2 grid, but you can have more than two versions of each factor. We're really only thinking about two factors at this point, but in theory, you could have more factors. Independence technically is when the factor frequencies are independent within one population. So that's looking within a population and thinking about two different factors. Homogeneity is when the factor frequencies are the same across multiple populations. So this would be like an example of looking at frequencies of blonde and brown and red hair color in multiple populations, like from different countries or something. So the mathematical calculations are exactly the same. The assumptions are exactly the same. The degrees of freedom is exactly the same. Rows minus 1 times columns minus 1. So really, for the purposes of this course, we're not going to make a big deal about independence versus homogeneity, because, for example, if you were to think about the height and gender example, is that independence, so it's height and gender within one population, or homogeneity, looking at height across two different populations, right? The males and the females. Or for the example I just mentioned here, looking at hair color across multiple different populations. So we're not going to worry about really the difference between independence and homogeneity. For the purposes of this course, they're basically the same thing. Now, this is an example of a chi-squared analysis that I actually find particularly interesting. What these researchers did is they were wondering whether the pupil size of the eyes on the face of a book would influence its ability to sell in a bookstore. So what they did was they created two versions of this book, one with the woman having large pupils, one with the woman having small pupils. And there's a reason to expect that pupil size is something that people notice, even if they don't realize it, because it's linked to things like fear and sexual arousal, both of which are aspects of our fitness in our evolutionary history. Anyway, so these researchers made two versions of the book, a small pupil version and a large pupil version, and then sold both of them kind of side by side in the bookstores or randomly assorted online. So then there was kind of a section at the back of the book where the person who bought it could go online and enter some basic demographic information about themselves and then provide a code that would let the researchers know whether that person had chosen or purchased the large pupil or small pupil version. Of course, in the bookstore, they're actually seeing the cover and picking it up. Online, it's basically being given to them randomly. And then here's what their data looked like. For bookstore purchases, they had male customers and female customers purchasing either large or small pupil books. Same thing for online. And then these are the numbers. And then they used a chi-squared 2x2 analysis, either with the continuity correction or without. But you can see they basically get very similar p-values here. In this case, there was a significant difference. In other words, the pupil size was not independent of the sex of the purchaser. And you can actually see that basically the males, there was kind of a skew towards purchasing the books with large pupils versus small pupils. Large pupils indicating either fear or sexual arousal, indicating that maybe males found this book more appealing when the woman was showing the sort of look in her eyes that is appealing to men. Females, there was this bias, but not as pronounced, right? This difference here was more in males than in females. There was not independence. On the other hand, online, where the people were not actually seeing different versions of the cover, you can see that basically the percentages they got were equivalent to whatever the percentages were in the warehouse, and there was a non-significant deviation between the observed frequencies and the expected frequencies. So the interesting result here is that the pupil size of the woman's eyes on these covers seemed to make males more likely to purchase the book, or perhaps females less likely to purchase the book, as evidenced by the non-independence between pupil size and sex of the purchaser. And actually companies do this sort of thing all the time. There's a lot of testing that goes into marketing. There's in fact a thing called split testing, where you present two different advertisements to the population. You look and see which one does better. In other words, which one maybe leads to more sales versus less sales, and then you refine your marketing iteratively like that. So marketers and companies that you deal with in your everyday life are constantly studying the behavior and choices of customers using models a lot like this one in order to make decisions about how they market their products and in fact how they design their products. Lastly, there's a special type of chi-squared test called the odds ratio or risk ratio, and this is when you have a 2x2 table, and generally this is used in public health where we have some sort of risk factor and some sort of non-risk factor and some sort of bad outcome and some sort of good outcome that we're interested in, and then we measure a number of people in each of these four categories. So for example, we could think about people who smoke versus people who don't smoke, and then measure of all of our smokers, how many have lung cancer, how many don't. Of all of our non-smokers, how many have lung cancer, how many don't. Or conversely, if we had a population of people with lung cancer and a comparative group of people without lung cancer, we could then survey them to see how many smoke, how many don't smoke, how many smoke, how many don't smoke. And then we can conduct a chi-squared 2x2 on that box there. And the calculation we're going to do is we're going to calculate the odds ratio, which is A divided by C. In other words, looking at the bad outcomes, how many are doing the risk factor versus not, divided by B divided by D, which is of the good outcome, how many have the risk factor versus not. And if this value ends up being 1, that would say the people with the bad outcome, whatever that ratio is the same here. You would get an odds ratio of 1. For our smoking example here, the calculation would be A divided by C, so 20 divided by 10 is 2 in the numerator. B divided by D, which is 2,000 divided by 3,000, 0.66. We would get an odds ratio of 3, and the interpretation of that is that smokers have 3 times the odds, essentially, of getting lung cancer. A related statistic is the risk ratio, which is calculated similarly in that it's a fraction of fractions. So this is looking at the risky factor, so how many have the bad outcome out of everybody in the numerator, and then looking at the non-risky factor, how many have the bad outcome out of everybody in the denominator. So for our smoking example, this would be 20 out of 2020 in the numerator, and then 10 out of 3010 in the denominator. Do that division and get a risk ratio of 2.98. And the interpretation of that is that smokers have 2.98 times the risk of ending up with lung cancer compared to non-smokers. So the risk ratio actually has a more clear interpretation, right? It's actually you're 2.98 times more likely to get lung cancer if you smoke than if you don't. The odds ratio, that 3.0, doesn't have that exact same interpretation. It's a little less useful. That being said, calculating confidence intervals for the odds ratio are actually pretty easy. So if you have odds ratio of 1.2, you could end up with a 95% confidence interval. These are fairly easy to calculate, and your lab manual shows how to calculate them. And you might get a confidence interval around 1.2. If it included 1, then you would know that this is a non-significantly higher odds, right? The data in the sample shows a 20% elevated odds, but since the 95% confidence interval includes 1, it means you can't rule out a genuine odds ratio of 1 in the population. On the other hand, if you had an odds ratio of 1.2 and the 95% confidence interval was from 1.1 to 1.3, then you would have a significantly higher odds of getting the bad outcome when you have the risky factor. Calculating confidence intervals for the risk ratio is not nearly as straightforward. So what we end up doing in published work is essentially people report both. The risk ratio is easier to interpret, but the odds ratio gives you these confidence intervals that allow you to figure out if it's a non-significant elevation or lowering of risk, or if it's a significant elevation or lowering of risk. Your lab manual has more detail about some of these calculations, and these really are reported quite a lot in the medical literature and public health literature. It is quite often that people will look at risky behavior, such as smoking cigarettes, or having unprotected sex, or having a certain diet, and then compare that to bad outcomes and good outcomes, like lung cancer, or STDs, or having heart attacks, things like that. So these odds ratios are actually used all over the place. They're also used in an intervention. If you do something to a group of people, you can then basically have, here's your intervention, here's your traditional method, non-intervention, then you look at the bad outcome, look at the good outcome, and you can see whether someone's risk or odds of having the good outcome and bad outcome differ in your treatment group or if in your control group.